So good work on the homework. So I graded questions 1, E and F, question 2, and question 3, all 4. So question 1 was taking some propositions and expressing them in the language of us. So let me pull up the book here.
Fixing this meeting room.
Don't. Well, you should always, well, I was going to say call or send an email. I'm not sure to whom. Yeah. But the more that they hear from people about it, the more likely the urgency will increase. I let Angela know, and she lets other people know, and it's an ongoing struggle, but I will put the fan up. That helps slowly. I think they say it's not a problem until it gets above 78 or something. Pretty
Yeah, not everyone will die until it gets to 78. So. Not an issue until 3 or more people die.
Alright, so question 1, you had 3 propositions, P, Q, and R, and then you were asked to write these other things as English sentences. And the main thing to remember here is that when you have an arrow like P arrow Q, that means if P, then Q. And you can really very literally just write down if, and then put in what P says, then put in what Q says. And sometimes the wording will be a little strange, but if you have the flu, then you miss the final exam. It's exactly what P arrow Q means. But if there's no arrow, there's no if then. So D, for example, P or Q or R says, you have the flu, or you miss the final exam, or you pass the course. And that is a proposition. It's a declarative statement. It's kind of a weird one, but it's not stating a conditional, like if this happens, then that'll happen. It's just saying you got the flu, or you're going to miss the final exam, or you're going to pass the course. So E was an or of 2 propositions. If you have the flu, then you do not pass the course. Or if you miss the final exam, then you do not pass the course. And we would word that differently, maybe, like, you know, if you have the flu or you miss the final exam, you're not going to pass the course. But as a strict interpretation, right, it's just mapping those things into there. So, didn't seem to be a lot of problems with that, except occasionally forgetting to put in the if or the then. And if you mean if then, you really got to say if then. Even if it sounds like an if then statement, make sure you say if something, then something else. I don't think there's any problem with the truth table question, other than make sure you show all of your work. If you just write down the truth table for this, and you write down the truth table for that, and you haven't shown the reader why the truth table you wrote for this is in fact the truth table, you haven't necessarily convinced the reader that those truth tables are meaningful. So you want to write down all the values of P and Q, and then write down what P and Q is. And then maybe write down a column for not P and a column for not Q, and then write down the AND of those, and then make a column for the OR of those two columns, and that should be true, false, false, true. And then ideally write a column for P arrow Q, write one for Q arrow P, and then write down the AND of those two. Or if you believe the reader knows the truth table for a P if and only if Q, just write that down. It should be true, false, false, true. And then if you just circle those two columns, the reader can see that they're the same values, and that convinces you that those two expressions are equivalent. And I think everybody got that perfect. So determine the truth value of each of these statements if the domain consists of all integers. That's important. For A and B, if they're true, give a specific example. For C and D, if they're false, give a specific counterexample. So determine the truth value for each of these statements. So you want to say either true or false for each of these. And I should have said additionally, if A and B are true, give specific examples. If C and D are false, give counterexamples. So what's the deal with this? A is saying there exists an integer x whose cube is equal to -1. Okay, if that is true, if you tell me that there does exist such an x, you should be able to give me an example of such an x. That's not always the case. There's some things we can prove there exists an x, but we can't actually find a particular x. Those are weird proofs. But there are cases like that. We know there's something that satisfies it, but we don't know what it is. But for this, right, I'm asking you, okay, give me an x. Prove that there exists an x by showing me an x that satisfies this. So you could say, you know, A is true, for example, x equals -1, and that's the value that everybody picked, which is good because that, you know, does have a cube that's equal to -1. For B, there is no integer for which x to the 4th is less than x squared. So for B, it's just false. Now, if you're not working over integers, you can find numbers between 0 and 1 for which this is true. This is why the set of numbers that you can pick x from makes a big difference. So for integers, B is false. And then C is saying for all x, the square of minus x is the same as the square of x. And that is true. For D, for all x, 2x is bigger than x, that is false. Well, if you tell me it's not true for all x, that means there's at least one x for which this fails. And so I'm asking you to show me an x for which this fails. And again, that's not always something we can do. But for this one, you can pick x equals 0, and 2 times 0 is not bigger than 0. Or more dramatically, 2 times -10 is not bigger than -10. -20 is smaller than -10. All right, so the only issue I consistently saw with the homework was not having it on 8.5 by 11 paper, or having the dreaded frilly edges on the edge. And so if you go back to the list of instructions for writing up homeworks, right, 8.5 by 11, clean edges, okay, is really important, because especially if homework is stapled, if your homework is on a slightly smaller sheet of paper, like 8 by 10.5, what happens? Your corner gets stuck in the staple of the paper in front of it, and while I'm flipping through grading, maybe I don't see it, you know, and so you get a 0 on the homework, and whoever had that paper in front of you, they get their homework, and they stuff it in their bag, and the homework is gone, you know. And same thing with frilly edges. They tend to grab other assignments, and they make a mess. So most frilly paper has, you know, a perforated edge you can tear off. I did that in a few cases. Or if you're pulling it out of a 3-ring binder, cut it, but then it's not going to be 8.5 by 11. So try to get, you know, 8.5 by 11 paper, clean edges. Engineering paper is great. Go in with 3 friends and get a pack from the bookstore and split the cost or something. Let me know if it's an issue. But other than that, homework looked great. Okay, so I think we're good on propositions and propositional logic. Which brings us to homework 2. So, homework 2 questions. So there's a batch of questions from 3.5, 3.8, and then some supplemental questions. posted an announcement to clarify things on these proof questions. So when you see something like this, everything to the left of the double arrow is a hypothesis. The thing on the right of the double arrow is the conclusion. So this first exercise is saying, given if A then B, if C then B, if D then A or C, and D, prove B. Okay, so you have 4 hypotheses here, and you're trying to prove that B is true. And if you want to do that with a direct proof, you assume if A then B, if C then B, if D then A or C, and you assume D, and you use the various rules of logic, direct reasoning, contrapositive, and so on and so forth, and try to prove somewhere in your line of arguments B. And then you can say QED. An indirect proof, you would assume your hypotheses, and you would also negate the conclusion. You would assume not B. And you would argue from there and try to get to a contradiction. And once you have a contradiction, then you can say, okay, so not B must have been false, so B must be true. And so for each of these, you can do a direct proof and an indirect proof. And be really careful that your indirect proof is actually an indirect proof, because it's possible to do an indirect proof as follows. I could assume my hypotheses, I could assume not B, and then I could do a direct proof of B, and say I've just proven B and not B. And that's a contradiction. Well, you really did a direct proof, and then you wrapped an indirect argument around it. That's not really what we're looking for, okay? We're looking for assuming not B, and then finding a contradiction. Other than if I directly prove B, that proves B and not B. So I was hoping that people made a stab at these and either had them all worked out or would ask questions today, since they're due Wednesday. Yeah?
Kind of like go over contradictions.
Yeah. Like indirect proofs?
Yep.
Okay.
Also do the last goes from the webinar.
The last what?
Also do the last goes like example from the webinar.
Yeah, that would be convenient. So you gave me 4 and 6. Let's do some from 3, because that's almost 4, right? So it's kind of like it's from the homework. Let's try 3A. So A implies B, C implies B, D implies A or C, and we've got D, and we claim that implies B. So I've just written 3A. Alright, so we're going to assume all of the hypotheses are true. So 1, if A then B. When I say A implies B, that's another way of saying if A then B. So this is a hypothesis. I'm also going to say if C then B, and I'm just going to assume that I need to use all my hypotheses, so I'm just going to write them all down rather than waiting until I need them. So I know those things are true. And I'm going to assume not B, that's the negation of the conclusion. And the idea is, by assuming that the conclusion is false, I'm going to find a contradiction. And therefore, I'm going to have to go back and conclude the conclusion was true. Okay, well, I've said B is false. But I also know that if A is true, then B is true. And I know if C is true, then B is true. But saying that B is false, logically, I can use that to show that A is false and C is false. Okay, so in the language of propositional calculus, we would say not A, and the reason is indirect reasoning between 1 and 5. So that's one of the rules on the purple sheet. If A then B and not B tells us not A. And similarly, not C, and that's indirect reasoning between 2 and 5. And I don't know if this is helpful or not, but it's kind of the only thing that comes to mind right now, so I'm doing this anyway. So I have not A and not C. This is true, and so their conjunction is also true. This is just the conjunction of 6 and 7. Well, up here I have a hypothesis with A or C over here on the right-hand side. Down here I have a proposition with not A and not C, and they're ANDed together instead of ORed. So that should tickle your De Morgan neuron. That should get you thinking, hey, wait a minute, I can get from here to there and back by using De Morgan's theorem. So let's just throw De Morgan at number 8. Not A ANDed not B is not C is the same as not A or C. And that's De Morgan's theorem applied to 8. Or you could apply De Morgan here. Well, we're set up for one more indirect reasoning. If D, then A or C, but we've also shown not A or C. That forces us to conclude not D. That's indirect reasoning of 3 and 9. And that's as far as we have to go because we've got a contradiction now. We've proven D and we've proven not B. And they can't both be true. So that's a contradiction between 4 and 10. Yeah?
Have you found that the syntax is a little bit different? Because at the end of mine, I put a 0, like the book does for its examples.
To say contradiction?
Yeah.
Yeah, that's fine. Okay. Or you could put an F for false, or you could write out contradiction. I would state where the contradiction is under the reason, and then maybe say therefore B, and then you could say QED if it fits. So most of these questions feel like this. You write down the hypotheses, you write down the negation of the conclusion, and then you do what you would do in a direct proof, but you hope that instead of proving something, you prove false, basically. You come up with something that can't possibly be true. And then you say, okay, so the conclusion must have been true. The direct proof of this is actually a little trickier, but the spirit of it is, if we know D, and we know D implies that, then we know A or C is true. And since A implies B and C implies B, A or C implies B or B, right? Which is the same as B. And so D actually implies B, and we've got D, so we've got B. But the formal language of that's a little confusing.
There is like a fast way to figure out which one you should, like what route you should take.
No, but the more you do it, the better you get at smelling out the right route the first time or the second time. But initially, it's totally trial and error. It's looking at what you have to work with, right? But the more you do it, the more you start to notice these things. Like, hey, anytime you have A implies B and you got A, let's just go direct reasoning and put in B. Or I'm trying to get something that involves a Q. Let me look at my expressions here that have a Q and try to work backwards from those. Right? It's kind of like running a maze backwards. You know, this is where you need to end up. Sometimes it's easier from that direction. But it totally just takes practice and trial and error. So other questions?
I was having a lot of trouble with C on the floor, and I mean, without going through that particular examples or anything you can pull out.
Are we trying direct or indirect?
Direct.
Direct. Well, the spirit of it, I think, would be this middle one, C and D. That tells us C is true. It also tells us D is true. We're also told if A is true, then C is false in the third statement. So the second statement tells us C is true. The third says if A is true, C is false. That tells us A has to be false. Okay, it's an indirect reasoning, although the right side has a negation. Well, if A is false, the first thing says either A or B has to be true. If A is false, B has to be true. So that's a pathway through. Now you gotta find the words to justify that, but I think that's probably the most direct proof.
So I guess when it's C and D, can we do like a next line to say assume C is true, and then another line that says assume D is true?
If it's C and D, you don't have to assume. You're guaranteed C is true.
Okay.
So I think that's conjunctive simplification. Conjunctive simplification says if P and Q are true, then P is true.
Okay.
So you can absolutely state C and you can absolutely state D, and then you can go from there. All right. Well, let's play with some more set theory. So let's talk about building sets from other sets. So let A be a set containing the integers 1, 2, 3. Let B be a set containing the integers 2, 4, 6. Okay, we can write what's called a union. It's a big U. And this is the set of all x such that x is in A or x is in B. It's the set of all elements x which are in A or in B. So for this particular A and B, what elements are in A and also in B, or in B? Is the element 1 in A or B? Is the element 2? Is the element giraffe in A or B? No, so giraffe is not going to be in the union. How about 3? So is 4, 5 is not in A and is not in B, so it's not in the union. 6 is in B, so it's in the union. And any other element you can think of is either not in A or not in B. So this is precisely the union. Now, the intersection, which is an upside down U, these are sometimes called a cup and a cap. This is the set of all x such that x is in A and x is in B. So what x's are in both A and B? 2. Anything else? That's it. That's all there is to unions and intersections. And by the way, we'll come back to this in a bit, but 3 elements, 3 plus 3 is 6. Union is 5, intersection is 1, 5 plus 1 is 6. There's a reason for that. We'll play with that. So what is A union with itself? going to be 1, 2, 3, right? Does it matter what A is? If I take any set in union with itself, I get the set of things that are in A or in A. It's exactly A. If I take A and I intersect it with A, that's a set of things that are in A and also happen to be in A. Well, that's just a set of things in A, right? What about A union the empty set? It's a set of things that are in A or that are in the empty set. Well, there's nothing in the empty set. So it ends up being just a set of things that are in A. A intersect the empty set, what's that going to be? That's the empty set because it's a set of things in A and also in the empty set. Well, there's nothing in the empty set, so there can't be anything in the intersection. All right, we have a set called U. It's the universal set. This is the set of all things. Well, it's not really all things. It probably doesn't have chocolate-covered giraffes eating broccoli inside. It might. But usually we have some idea of what the universe is, the universe of all integers. Well, in that case, U would be the same as Z. Or the universe of all C programs. Well, that's a big set. But it's got every C program in it, but it doesn't have whiteboard erasers in it. Yeah. That's my attempt to draw a fancy U. Let's not be so fancy. Let's just do a U. It's supposed to be a stripped U. So go like that.
Kind of looks even fancier.
Yeah.
I like the scribble.
But it's mainly just separated from the union symbol of the little pigtail. So what is A union with the universe? The set of everything that's either in A or in the universe, the set of all things. That's just the universe, right? And A intersect the universe, the set of all things that are in A and in the universe. That's just A. Do these look familiar at all? What do they look like?
Like and or symbols?
Like what?
Like the and or symbols?
Like the and or symbols.
They're kind of like the stuff I read.
Stuff from algebra. We saw these in Engineering 250. If you replace intersection with and, union with or, empty set with 0 or false, universe with true or 1, you get our identities from Engineering 250. We also got these a couple of weeks ago in this course. We said things like P or P equals P. P and P equals P. P and false equals false. P and true equals P. And so on. There are so many parallels in all stuff, but especially in computer science classes. Set theory, propositional logic, Boolean algebra. If you do mathematics, group operations, these parallels cut across disciplines. And there's good reasons for that. But it should feel somewhat comfortable. we've got unions or ors, we've got intersections and ands. What are we missing? Negations. The negation of A equals the set of all things in the universe such that X is not in A. The negation of A is basically everything that's not in A. Well, this depends on our universe. So if the universe is the set of all integers, and A equals our set 1, 2, 3, then the complement of A equals something like this. All the integers except 1, 2, 3. So let me note this. This is the union. This is the intersection. And this is the complement. And sometimes this is written as A with a little c on the top. Just like in 250, sometimes we use a quotation mark instead of a bar, because it's easier to type that way. There's another version of a complement. This is the complement of A in B. And this equals a set of all things not in the universe but in B, which are not in A. So the complement of A and B is start with B, throw away anything that's in A. So it's basically everything not in A, but you're only looking inside B. And this is sometimes written as B subtract A or B take away A. And so a complement of A is really just the universe with A subtracted from it. It's the complement of A in the universe instead of in some arbitrary set B. Well, that's usually what we mean, so we usually have a special symbol for it. A bar is just the complement in the universe. B minus A or B slash A is the complement of A in that set B. And so we have more properties. Like the complement of the empty set is the universal set. Everything that's not in here, well, that's everything. And the complement of the universal set, everything that's not in the universe of all things, well, there's nothing that's not in the universe, so the complement is the empty set. And the complement of A will turn out to be just A. You start off with a set A. This is the set of all things that are not in A. This is the set of all things that are not in the set of all things not in A. And that's a mouthful, but if you work through it, it turns out to be everything that's in A. So we got unions, intersections, and complements. Where do we go from here? What's the only reasonable place to go? If you're a nerd like me. To Morgan. Morgan pops up here as well. The complement of the union is the same thing as the intersection of the complements. And symmetrically, the complement of the intersection is the union of the complements. and that's 250-ish, and that's propositional logic-ish. Alright, how many people here are familiar with Venn diagrams? Yay! Google had a Google Doodle for Venn's birthday a couple of years ago. So Venn diagrams are a pictorial, a graphical way for us to represent some of these set operations. So if this is a set A, and this is a set B, this area here, this is the intersection. And all of this stuff, all of this stuff everything contained in here, that's the union. So the union would be everything inside those two circles, including the overlap area. The intersection is just the overlap area, right? And logically, you put some dots for the elements of A and for the elements of B. Anything that's in here belongs to both of these circles, so it's in both sets A and B. That's the intersection. So that's why we can think of that way. The complement of A would be everything that's not in A. So it's all of this stuff. Everything that's not in A. Well, we usually need some kind of bounding box here, so we generally have the whole universe shown. And then the complement of A is everything in the universe that's not in A. And sometimes Venn diagrams help us visualize what's going on with set operations. And you can kind of maybe convince yourself some of these theorems using Venn diagrams. Like, A union B equals B union A, commutivity. Well, that's pretty obvious, right? Or the intersection of A intersect B is this area. Well, B intersect A is also this area, right? So that makes sense. The complement of A is all this stuff outside of A, right? The complement of that is everything that I haven't marked here. Well, that's just the stuff inside A. So that's why A complement equals A. De Morgan's theorem is a little trickier, but you can draw pictures of A union B complement and pictures of A complement, intersect B complement, and argue your way from there. But Venn diagrams are not proofs. Okay? They're ways that we can get some insight into what's going on, and that might help us construct a proof. But drawing a picture like this is not a proof, because what if A wasn't a circle? What if it looked like this? Or if A was bigger than B? Or A and B had some different relationship to each other? So we can't prove relationships about sets using Venn diagrams, but they can help us sort of get some insight into what's going on sometimes. All right, last thing is, did we talk at all about this last time? A inside vertical bars, the number of elements in the set.
Oh, yeah, we told you.
Okay.
That's cardinality, right?
That's cardinality. So vertical bars on A, that means the number of elements in set A. So then we call that the cardinality of A. So the cardinality of A is 3, cardinality of B is 3. Cardinality of their union is 5, because there's 5 things in that set. Cardinality of the intersection is 1. But the idea that this is the number of elements only works if A is a finite set, if it has a finite number of things. If it's something like Z, it has an infinite number of things. So the cardinality is not infinity, because that's not a number. but we'll talk about what that cardinality is either later today or Wednesday. And this vertical bar symbol, you've seen this before? Where have you seen this used? Absolute value. Vector magnitude. And now set size or set cardinality. It's a common symbol. It pops up again and again in different areas, but it always kind of means the size of something, right? -1 million, yeah, it's a really, really negative number, but somehow it's big, right? It's really far away from the middle of the number line. It's as far away as +1 million, right? So if we measure the size of a number as how far it is from the middle of the number line, the absolute value gives us that size. When you have a vector, you might have a velocity vector that's pointing in that direction, or pointing up in that direction, or pointing off at an angle, and your car might not be moving at all on the road, but it might be flying up in the air really fast. If you want to know how fast it's moving, it's not just the speed in one particular direction, it's really the magnitude of that velocity vector. And if you're going off at an angle, it's a combination of how fast you're moving in the 3 different directions, with some squares and square roots and stuff. So this is kind of a universal symbol, but depending on your domain, it means different things. And for a set, it's basically how big the set is. For finite set, bigness is determined by how many things are in it. For infinite sets, bigness is a very different thing. Because the set of integers is very big. The set of rational numbers is very big, fractions. The set of prime numbers is very big. But they're all equally big in some sense that we'll make precise. The set of real numbers is very big, but it's bigger. It's a bigger big than the set of integers in a way that will make precise. But this notion still somehow measures the size of things. So cardinality will add a lot more detail to later today, probably tomorrow, because I want you to work on a homework set next. So I have some homeworks here to work on in groups at the board. And the first question is define 2 sets containing a few elements, whatever you want to put in there, and then calculate their union, intersection, and the complement of one and the other. Okay, so A take away B and B take away A. And try to make sets that, have some things in common and some things not in common, so that they're kind of interesting. Don't just pick A and B to be the empty set, because that's a little too easy. Okay. Question 2, we've got 2 specific sets, X and Y, and U is a set of all uppercase letters, and play around with some Venn diagrams. Right, sketch circle to represent X, one to represent Y, and then figure out which regions are the intersection, the union, and so on and so forth. So just practicing with that. And then for those same sets, A and B that you used in one, calculate the size of the union, calculate the size of A plus the size of B, and follow those instructions. And I think we're going to skip question 4 for now. So play with these first 3, and then we'll talk about question 5, and I want you to work on question 5 after that. So I'll leave these up here. Find some people to work with, find a spot on the board, and work on these first 3. You put them all over, you really want to calculate it. Actually, that's exactly what it is. So, would A union be equals? I think we don't want that. It's complementary. Yeah, I meant I think it's sort of like what I mean is also calculate A complement B and B complement A. So A subtract B, B subtract A. Okay. That's what I'm saying. So it's going to be A backslash B. So X times all Y would be X union Y. Maybe that's what it is. Okay, so B that's not A. So it's just minus Y. Oh wait, yeah. So that's everything is X. So everything X is not in Y.
That's so fine.
Saying the concept, so we're this like we're going to do it hard, then you go with and then both is that it or that's it's already
see to make everything.
All right, so I'm going to stop you at this point and switch gears, because I think everybody gets the idea of this. If if you didn't get all the way through 3, I think everybody got Venn diagrams and they look good. If you didn't get through 3, we're going to come back and talk about this a few times anyway. But let me talk about question 5. And you can stay where you are if you want, but let me talk you through this because we have about 20 minutes left, and I want you to work on this. So, question 5 is something that we call Russell's paradox, and it deals with a funny definition, which is the definition of a set as self-consuming. Yeah. I will in a minute. Oh, yeah, thanks. So what does it mean when a set is self-consuming? A set is self-consuming if it contains itself, okay? This is a strange thing. So for example, here's a set of all integers z, and we know that the number 5 is an element of z. And we know that a smiley face is not an element of z. So there's some things that belong to this set, there's some things that don't belong to this set. Okay? So we can ask, is this set of integers an element of the set of integers? And it's not. Right? This doesn't contain any sets. It only contains 1, 5, 10, -6, 0, 2,019,000. But it contains integers, right? It doesn't contain any sets. I could have a set consisting of z and r, and that would contain z. But in fact, z is not an element of z, which is not surprising. So z is not what we call self-consuming. And it's very hard to think of a set that is self-consuming, because how do you put a set inside itself? Okay, but that doesn't stop us from making a definition. It's like a definition of an elephant that can fly. Well, if no elephants can fly, I can still make a definition of that, right? So a set is self-consuming if it contains itself. Okay, so that's the definition we're working with. Okay, so a set is self-consuming if it contains itself. Okay, so part A, define a set B, which is all the sets that are not self-consuming. Well, we already know one set that's not self-consuming, that's Z. So we know that Z is an element of B. We had a set A, which was equal to 1, 2, 3. And does this contain itself? I don't see an A anywhere in here. So A is not self-consuming. So that's also going to be an element of the set B. So B is going to be the collection of all the sets that are not self-consuming. Got that idea? Okay, self-consuming means it contains itself. B is all the sets that are not self-consuming. Okay, so identify 5 elements of the set B. Well, I already identified 2 elements of the set B. Z is not self-consuming, A is not self-consuming. All of the sets that I see written on the board, none of those sets contain themselves. Right? A contains Malcolm and a square and chicken tenders and true, but it doesn't contain A. So A is not a self-consuming, that set's not a self-consuming set. Are there an infinite number of elements in B? Are there an infinite number of sets that are not self-consuming? What do you think?
Yes.
Why?
Is there an infinite number of sets?
Yeah, there's an infinite number of sets, and just about any set we can think of does not contain itself. I could just pick sets of integers. I could say all the integers bigger than 1. Well, that's not self-consuming because it doesn't contain any sets. All the integers bigger than 2, that's a different set that's also not self-consuming. So there's an infinite number of things in B. Okay, so here's the real kicker. Is B a self-consuming set, or is it not a self-consuming set? So pick one of these and see where that leads you. Assume B is self-consuming, or not, right? And see where it leads you. So that's what I want you to spend about 5-10 minutes in your groups talking about, working out on the board, thinking about. So explore this question. Is B a self-consuming set? Exactly. Oh, this is what Kirk used. That's how you, oh really? Okay. Self-consuming, that should be in here. Any test not self-consuming is in here. So it's either simultaneous and be a in the last 3 minutes. So as you probably discovered, there's a problem here, all right? The problem is B equals the set of all S such that S is not self-consuming. If B is self-consuming, then B cannot be a member of S, because this contains things that are not self-consuming. So if B is self-consuming, it's not contained in B. Well, if B is not contained in B, this means B is not self-consuming. So if we assume B is self-consuming, we're forced to conclude B is not self-consuming. It's a contradiction. So we must conclude B is not self-consuming. Well, if B is not self-consuming, this is a set of all sets that are not self-consuming, so B must be contained in B. Well, if B is contained in B, B is self-consuming. And so if B is self-consuming, we can prove it's not self-consuming, and if B is not self-consuming, we can prove it is self-consuming. That's the paradox. And the example I was just looking at over there is if you wanted to make a self-consuming set S, we could try to do this. Well, S is a member of this set. But this set itself is not contained inside here. This contains S, but it's missing this thing, which is what we said S was equal to. And this set itself, curly bracket S, comma, curly S, curly, curly, is not contained in here. We got that and we got that, but to be self-consuming, it's also got to contain this. But as soon as we add that in, it's not containing itself anymore, because this set is not in these three things that I just wrote. We got to add a fourth element, which would be this. And if we try to construct this, we keep having to add more and more elements. And the notion that this is a well-defined definition of self-consuming leads to this paradox. So this was the result of what's called naive set theory. This was pre-1900 set theory, where sets were just collections of things. What sorts of things? Animals, geometric shapes, integers, doesn't matter. So we just make it a collection of sets that aren't self-consuming. Axiomatic set theory, the rigorous version of set theory, prohibits that. Because if we have this kind of loosey-goosey notion of a set is just a collection of things, we can create paradoxes like this. And so this is called Russell's paradox. Right? And Bertrand Russell, this is named after him. And it's one of many paradoxes we can get into from naive set theory. This is what launched my life down a different path, like 34 years ago. But I'm still on. My research interests kind of evolved out of this exact paradox in a variety of different forms. If you watch original series Star Trek, when Harry Mudd is working with the androids to take over the Enterprise, and they use I'm telling a lie riddle to overload the brain of one of the androids, that's this. That's Russell's paradox. Everything I say is a lie, and then you say, I am lying to you. And if everything you say is a lie, then that statement must be a lie, which means you're telling the truth, but you can't tell the truth because everything you say is a lie, so you must have lied, in which case you were telling the truth when you said you were lying. It's exactly the same thing. And we're going to use this in another form called diagonalization on Wednesday to prove that the number of real numbers is somehow fundamentally bigger than the number of integers. And that's going to lead us to the idea that there's different versions of infinity. There's big infinities like the number of integers, and there's really big infinities like the number of real numbers. And they're fundamentally different sizes. And we can prove that using this same thing with some really clever arguments called diagonalization. All right, so Wednesday we will get to story time, and I'll tell you about Hilbert's Grand Hotel and Blauman's Grander Hotel, and we'll continue down the path of set theory. Let me know if you have questions on your homework. Bring those to turn in on Wednesday. I will see you next time.